Hey, Physics 111. All right, so this is the first recorded lecture for chapters 10 and 11. I'm just going through them sort of all together. They kind of all fit together, so I'm not going to distinguish between what's chapter 10 and what's chapter 11. All right, so these chapters are about rotation and angular motion. So this is when we're talking about an object. We have sort of two different situations. One, you might have an object where it's spinning around an axis inside of the object itself, right? So the Earth spins around a line that goes through the North and South Pole and through the center of the Earth. A record player or a CD or a hard disk, our hard disk would spin around sort of central axis. And that's got angular motion, rotational motion. It's rotating around it. Another situation is where you might have an object. So here I have some object here, and it's moving around this central location, some central point. And so it's moving could go a whole circle. It doesn't have to go a whole circle. So uniform circular motion would fall under this, but uniform circular motion required that we have a constant speed. The amount of the velocity as this thing moves around a circle would stay constant. That doesn't have to be true. That just has to be true if you're talking about uniform circular motion. So this is a more general case where we just have this object, and again, it's orbiting or revolving around some point. So rotation, technically, in a physics kind of way, is sort of spinning, or the more typical term for that one for laypersons would be spinning, where you'd be spinning around some axis which is inside of your body, whereas revolving is probably closer to what we think of as orbiting, where you're going around some axis which is outside of the body of the object, right? So here, this is a spin where the axis is inside the actual object. And here, this is a revolution, although this could also sometimes be called a revolution, or orbit, where you go around some outside axis. All right, so this is not linear motion. This is angular motion. But a lot of the ideas that we had for linear motion, we can still use for angular motion. So when we talked about linear motion, we had position, which was x. We had an x naught, and we had x final. Now we're going to have angular motion. So we're going to say, okay, well, say I've got a blade of a fan, and it moves from some position here, right? So this is the initial position of the blade of the fan. And I can say that's theta naught. So that's my initial position. And then the blade of the fan, after 2 seconds, is a very slow moving fan, moves to here. And that's a different angle. So this is not an X and Y position, right? It's moved up like this in an angle is what it's moved, right? I could actually say, well, what if this is, 0 degrees, and then theta final, that's like 45 degrees. And I'll say we do usually do this in radians. So 45 degrees is pi over 4 radians. Right, the whole thing is 2 pi. Halfway up is pi over 2. So a quarter of the way through the first quadrant is pi over 4. So this is called angular position. And it is usually written in units of radians. So it can be a decimal, but radians again are the pi things, right? And if you have something in degrees and you want it in pi, remember that 2 pi radians equals 360 degrees. And so you can use that as your conversion factor if you had something, say, in degrees and you needed to turn it into radians. Angular displacement is the delta theta. So we used to have position, which was x naught, and and x final. And then we had displacement, which was delta x. Now we have delta theta, which would be theta final minus theta initial. We used to have velocity, which was the derivative of position with respect to time. Now we have angular velocity. Angular velocity is written as this little sort of funky looking W. It's actually the little letter omega. It's the lowercase omega. And so I call that omega. Omega equals the derivative of position with respect to time, just as our regular translational or linear velocity was the derivative of position with respect to time. Now our angular velocity is the derivative of angular position with respect to time, where the average angular velocity, the average omega, again, would just be the displacement, the angular displacement now with respect over the time it took to do it. And so everything that we had before, we have again. We just put angular in front of it, and that requires that we have new variables that go with it. Omega is going to be in units of radians per second, and so would omega average, obviously. And just as before, when we had acceleration, right, linear acceleration was the derivative of velocity with respect to time. Now we have angular acceleration, which is alpha. Which it's the derivative of angular velocity with respect to time. Unit-wise, this is going to be radians per second squared. So we're just missing the meters at the top, right? Because this is an angle. How many angles per second? How much of an angle per second is it moving? How much is the angular per second speed changing per time? That's what angular acceleration is. And so back in chapter 2, we had these 4 equations for linear motion. Right? These are our big 4 equations for linear motion. Now we're going to have their analogous equations for angular motion. We're going to have every time, anywhere we had v, we're going to have an omega. Right, so here's V final, now we have omega final, V initial, now we have omega initial, and any place we had A, we're going to have alpha. Any place we had X, we're going to have thetas. So we had X final and X initial, now we have theta final, theta initial. And essentially that's where these equations come from. So this is 2 alpha, theta final minus theta initial. In any equation we had in the past, we now have for angular motion. And so these are the 4 equations we're going to use for some of the things we need to solve in our homework from chapter 9. An important thing to remember here, when we did one-dimensional motion, right, if we were doing x, we had to sit there and we had to say, well, this is what I'm going to call my positive x. And anything that was going the other way would have had a negative value in here, right? If V naught was actually this way, then we would have had a negative V naught. So when you do these equations, you have to sit there and say one way is positive and one way is negative. In angular motion, this is going to be a distinction between either going counterclockwise or clockwise. Right? With one-dimensional motion, it's either you go left or you go right. So you go right or you go left. But now we're going to have, this is angular motion, and so we're going to have counterclockwise and clockwise. And believe it or not, counterclockwise is going to be positive. We don't get to choose in this. You do not get to choose like we did with the x, where you could choose which way you wanted x to be positive. No, you don't get to choose. As the book says, clocks are negative. Angular displacement in the counterclockwise direction is positive. And that's going to be true for any motion. So the direction of delta theta, omega, alpha, and all the other things that we come across that have to do with motion in angular motion, counterclockwise is positive, clockwise is negative. And so I usually just write CCW for counterclockwise and CW for clockwise. Remember that clockwise, the way a clock works, is negative angular motion. There's a right-hand rule that goes with this. I don't want to talk about it. All right, a brief aside here, which is relating angular velocity variables like delta theta and omega and alpha to actual sort of lengths in linear variables. So if you had a situation like down here, so say you had something that moved, like our fan blade, it moved from some initial location here to some final theta there, and I wanted to know how far did the end point move. So here's the end point. It moved all the way along this arc. So we call this an arc, right? An arc is this part of a circle. If it was the whole circle, right, that it would be the circumference, and we'd say 2 pi times r. Well, 2 pi would be the delta theta of a whole circle, right? So if this was a whole circle, then the whole circle, the length that I just did there would be 2 pi r. If it was a whole circle, then the delta theta would be 2 pi. And so all I've done is I've taken the delta theta and I've multiplied by r. If you don't go to all of 2 pi, if your delta theta, say, is this, when I say that was, say my delta theta here is 3 pi over 4, then I would still just multiply that. This length s here would just be r 3 pi over 4. So I multiply by r, and that tells me how long the arc length actually is in meters, if I put it r in as meters. That's why the circumference is 2 pi r. It's because the arc length is how far around did you go, how far around is your delta theta, and then multiply by r. Similarly, if I wanted to know how fast, what is the actual speed, tangential, instantaneous speed that an object has if it's on the edge of something that's spinning or it's moving around at some omega. So there's some omega sort of angular velocity here that this thing is spinning around at. And again, this object is r away from the center. If I want to know the tangential speed, then I just multiply r times the omega. So to get the actual length, I multiply r times the angular displacement, and I get a length. If I want to know the actual speed, I multiply r times the angular speed, and I get the tangential speed. This is the same as v. We used to say that our v was 2 pi r over p if omega is constant, so that it's actually equal to 2 pi over p, which is what omega would be equal to, right? It would go, p is the time it takes to go one time around. It's the period, and then 2 pi would be the angle of going one time around. There's also tangential acceleration, a sub t, which is going to be r times alpha. This exists along with our old friend a sub c, the centripetal acceleration. So if an object has actual angular acceleration, that means that omega is not constant, right? Alpha is the derivative of omega with respect to time, and so if alpha is not 0, then that means that omega is not constant. That's a double negative there. So in that case, you'd have tangential acceleration plus our old school centripetal acceleration. And in fact, the acceleration our object would have would be the vector sum of our acceleration from that goes towards the center of the circle, and then this, which is at 90 degrees to that, right? So if I actually had some object moving around in a circle, and say it was here, it would feel some centripetal acceleration this way, but it could also feel a tangential acceleration this way. And so its total acceleration would be the centripetal acceleration towards the center of the circle, and its tangential acceleration tangentially. If omega is constant, like we dealt with back in chapter 4, and then when we dealt with uniform circular motion, then that means that alpha is 0, right? Alpha is the derivative of omega with respect to time. If this is constant, then alpha would be 0, and so the tangential acceleration is 0, and so you only have a sub c, and you have uniform circular motion. So that's a special case, as we were saying it before. All right, let me do number 9 real quick, and that'll be the end of this video, and then I'll come back and do another example. So number 9 says that I have a drum that rotates around a central axis at an angular velocity of 12.60 radians per second. If the drum then slows at a constant rate of 4.2 radians per second squared. All right, so it says the words even, which is great. It says angular velocity of 12.60 radians per second. So this is an omega. And then it does say if the drum then slows at a constant rate. So this is the initial omega. This is the initial angular velocity. It then tells me it slows at a constant rate of 4.2 radians per second squared. Though it says it slows at a constant rate, and then it has the units for angular acceleration. So this is alpha. And it says slows at a constant rate. So that means that this thing, omega naught and alpha, need to have opposite signs. And so I'm gonna go ahead and just say this one is positive and this one is negative. I could have said this one was negative and that one was positive, that omega was, but it feels weirder that way because it's not telling me whether it's clockwise or counterclockwise in the problem. So I'm just going to say that this is positive and that the angular acceleration is in the opposite, the clockwise direction. All right, so then it says, how much time does it take? It slows at a constant rate. And through what angle does it rotate in coming to rest? And there we go again, to rest. And just like when we did linear or translational motion, rest means 0. All right, so part A says, how long does that take? So time. So I literally am going to go look at my equations. We have to go back in equation shop. I know, and this is the easiest one, I know omega final, I know omega initial, and I know alpha. So I can straight up use my first equation. So omega final equals omega initial plus alpha t. Move this all around. And plug everything in. Right, I end up with a 0, subtract a 12.6, and then divide by a negative 4.2. So I have a negative 3 divided by a negative 4.2. Sorry, negative 12.6 divided by a negative 4.2, and it gives me 3 seconds. Part B, through what angle does it rotate to do this? So that is basically saying, what's the displacement? How far does it go? What angle does it rotate? So it wants to know delta theta, or theta final minus theta initial. Well, now I know a lot of things. I know time, I know omega final, I know omega initial, I know alpha. So I could use a lot of different equations here. Probably the easiest one would be just this one. But again, any of these other three would do. I'll use that one. So omega final minus omega initial is equal to 1/2 omega initial, theta final minus theta initial equals 1/2 omega initial plus omega final times time, and putting those numbers in. And I get 18.9, and again, that's in radians. So I need to write out the radians there. All right, so that's number 9. I'll end this one here, and I'm going to come back, and I'm going to start, and I'm going to do example number 19.